Hi everyone, my name is Hamid Gorgiara from UC Irvine, and today I'll be presenting Jaaru, an efficient model checker for persistent memory programs. This is a joint work with Hari Zhu from UCLA and Brian Dembski from UC Irvine. Modern software frameworks from cloud-based big data platforms to personal software applications rely heavily on memory and storage to offer their services. These frameworks use DRAM for keeping any frequently accessed information, such as the working data and the program code, and use storage for saving the state of the program and any data as files for future inquiries. Recent persistent memory technologies, such as Intel Optane memory, attempt to bridge the gap between DRAM and storage by providing the performance and flexibility of DRAM with the persistency of flash storage. Persistent memory can interface with the processor via the memory bus, which provides byte addressable access for a program with regular load and store instructions. These instructions bypass the OS kernel and offer a flexible and efficient interface to storage. With persistent memory, the program can use a single copy of data structure both as an in-memory working data and as a persistent store of data. This new way of data manipulation is very efficient in terms of memory usage and eliminating the overhead of serialization and deserialization process. However, this efficiency comes with the main challenge of system crash happening when the program is running. This is challenging because stores are not immediately written to persistent memory. They are initially written to the volatile processor cache, and the persistent memory is eventually updated when the cache line is written back due to space constraints. So the order a write becomes persistent can be different from the intended program order. Modern processors provide special cache instructions such as CL-flush and CL-write-back to force the ordering by flushing cache lines to persistent memory. However, using these instructions correctly is challenging and error-prone by itself. It requires both subtle reasoning about the ordering of memory operations and attention to not miss persisting of any stores in the program. So testing the correctness of persistent memory programs with respect to failures is very difficult. This is because exposing a bug requires the machine to fail at a specific instruction and depends on the state of the cache line before the failure. There has been a lot of tools implemented for testing and model checking persistent memory programs. Some of these tools need users to add extra annotations for different cache line flushing properties, which not only incur burdens on users, but also are error-prone themselves. Consequently, if the developer misses an annotation or adds an incorrect annotation, the tool will have false negatives and miss real bugs, or have false positives and report bugs that aren't real. Violations they report are with respect to design principles and may or may not correspond to actual bugs. For example, certain tools report data has not been flushed. However, in some cases, the data will never be accessed by future executions. So the absence of a flush is a false positive that does not represent a real bug in the program. Most of these testing tools do not test the recovery procedure and dismiss the possibility of occurrence of system crashes in the recovery code. Some of these tools are testing based and only test the running example, and they require a test suite that covers all testing scenarios to fully test the program. These drawbacks call for a new testing tool that can exhaustively explore states without needing manual effort, and it can find real bugs in the program. Based on this need, we implemented Jaaru, a fully automated model checker for persistent memory programs. Jaaru has the goal of exploring the post-crash executions for every post-crash state to find crash consistency bugs in the program. However, developing such model checker is very challenging in practice. In fact, a recent technique called YAT attempts to use an eager model checking approach to enumerate all possible post-crash memory states for a persistent memory program. This approach is not practically scalable because the number of memory states that must be explored grows exponentially with the number of stores that have not been flushed to memory. We investigated persistent memory programs and we made an observation that makes model checking practically feasible for them. In fact, we observed that these programs need a way to verify the progress of pre-crash executions and determine which data has been written out to persistent memory. One common technique is to write a checksum with data and in the recovery procedure, read that checksum to verify that the data was persisted correctly. Another technique is to use commit stores. These commit stores indicate that prior stores have been successfully flushed to persistent memory, and in post-crash, the program just reads from these stores to determine the data is consistent. For example, there is a tree data structure, and we want to add a subtree to its root. First, the program creates new nodes and properly updates their values and references. Then, the newly created subtree is being flushed to the persistent memory. Finally, the program updates the pointer from the root of the tree to the subtree. This pointer is a commit store. In post-crash execution, if this pointer isn't null, it shows the insertion operation was successful. But if the pointer is null, there is a lot of possible memory states in post-crash, but all these memory states correspond to one unique post-crash execution, and that is the insertion operation failed, and the program needs to recreate and reinsert the subtree. Commit store pattern is very common in data structure implementations because first, the information about consistency also provides a reference to where the data is stored. And second, for the efficiency purposes that prevents the post-crash execution from accessing many unflushed stores. Our insight is to leverage commit store pattern and enumerate executions instead of memory states to make model checking practically feasible. Based on this insight, we implemented Jaaru to exhaustively explore all possible executions to find crash consistency bugs in the program. Jaaru doesn't require any annotations or modifications on the existing program. Also, it does not generate any false positive or false negatives. Any bug it reports is a real bug with the corresponding execution trace leading to the bug. Jaaru is capable of simulating complicated crash scenarios with more than one crash for testing the recovery code. It uses a constraint-based refinement technique to reduce the search space. The idea is to reason about the last time each cache line was written back to persistent memory. To be more specific, Jaaru uses CLFlush instructions to infer constraints on the last time each cache line became persistent in a pre-crash execution and refines these constraints in the post-crash execution to narrow down when a cache line is written back to memory. As an example, the program executes the instruction sequence on the left-hand side prior to the failure. Both variables x and y are located in the same cache line. The blue line shows the order that stores were written to the cache. After the program executes the store y equal 1 and x equal 2, it performs a CLFlush instruction. This instruction flushes the cache line that holds x and y to the persistent memory. At this point, Jaaru infers the constraint that the cache line for x and y was most recently flushed during the interval from CLFlush to infinity as represented by the red line. After the CLFlush, the program performs the stores y equal 3, x equal 4, y equal 5, and x equals 6. Finally, power is lost and the program fails. The red interval indicates that when the machine is powered back up, the persistent storage may have the values 2, 4, and 6 for the variable x, and 1, 3, and 5 for the variable y that the post-crash execution potentially can read from. Suppose the post-crash execution, which you can see on the left-hand side, reads the value 4 for the variable x. This tells us that the cache line must have been flushed sometime after the store x equals 4 and before the store x equals 6. So we can refine the interval for the most recent flush to be from x equals 4 up to but not including x equals 6, which imposes a much tighter bound on the cache line's interval. Now, if we read from the variable y, the program only can read the values 3 and 5, and it doesn't see the store y equal 1 anymore. Our constraint refinement approach works well for persistent memory programs because it effectively leverages commit store, which is a common technique to achieve efficiency. In fact, Jaaru does not eagerly enumerate all pre-crash stores. Instead, it lazily enumerates a small subset of them that are actually read by a post-crash execution. So in our previous example, if there was a variable z with multiple writes in the pre-crash execution, but the program never reads from them in the post-crash execution, Jaaru does not enumerate executions for different values of z since it doesn't expose any new behavior in the post-crash execution. This technique yields extra efficiency for Jaaru in pruning the search space to avoid exploring redundant executions. In fact, the complexity of Jaaru model checking programs that use commit stores is O of m squared, where m is the length of the execution. We obtain this complexity because the number of crash injection point is O of m. The post-crash execution involves O of m steps, and with commit stores, we explore two executions at each crash point. That is, a first execution that reads from the commit store, and a second execution that reads from the value of the memory location before the commit store. If a program does not use commit store pattern, still it can benefit from Jaaru to reduce the search space compared to naive model checkers. In fact, in a naive model checker, if n different cache lines have unflushed stores in the pre-crash execution, then the number of post-crash states is at least 2 in power of n. The majority of persistent memory-based tools have been developed for x86 since it provides the most advanced and mature architectural support for accessing persistent memory. So we have implemented Jaaru, which incorporates a full simulation of TSO memory model, including support for store buffering, buffering flush instructions, and buffering expense instructions. The CL flush up instruction can be reordered with other CL flush up, previous stores to other cache lines, CL flush instructions to different cache lines, and later stores to any cache lines. Support for reordering CL flush up with other instructions is implemented by a flush buffer. Both store buffer and flush buffer are emptied on execution of mfence or lock read modify write instructions. To use Jaaru, the persistent memory program has to be compiled with Jaaru's LLVM frontend, which instruments memory and cache instructions. Then, after running the program, the scheduler identifies potential crash points and the runtime system runs the program and simulates crashes. Jaaru analyzes the executions and refines the corresponding constraint for each cache line. If it finds bugs in the program, it reports them to the user. Otherwise, it repeats the process until there are no more new executions. Jaaru supports two popular APIs for accessing persistent memory, libpmem-malloc and libpmem. Jaaru can identify different types of bugs, including missing fences, misordered flushes, missing flushes, and misordered stores that cause atomicity violations. We've evaluated Jaaru with PMDK and recipe benchmarks, and we found 25 persistency bugs that 18 of them haven't been reported before. PMDK is a mature library developed by Intel for accessing the persistent memory, and we found 6 new bugs in PMDK. The majority of these bugs are in the core libpmem object library in PMDK and cause assertion failure or illegal memory access. Some of these bugs are atomicity violations in which partially completing updates leaves the data structure in inconsistent states. Recipe is a collection of concurrent DRAM indexes for persistent memory, and we found 12 new bugs in 6 recipe programs. These bugs were caused the program to crash or loop, and there were cases of missing flushes, using non-persistent data structure, and atomicity violation. All of the bugs can potentially corrupt a persistent data structure, leading to the data loss. We have fixed the bug and used Jaaru to look for additional bugs until the program executed correctly. At the end, Jaaru can model check each recipe program in less than 15 seconds. Compared to previous model checkers, Jaaru reduces the search space orders of magnitude, and it is much faster. For instance, for PART program in recipe benchmark, Jaaru only explores 174 executions compared to YAT, which needs 10 in power of 34 executions to fully model check the program. To conclude, testing a persistent memory program is very challenging, and it's very important to verify the correctness of a program with respect to failures. As a solution, we presented Jaaru, a fast and fully automated model checker that explores all possible executions, and it can find real bugs in the program. Based on our evaluation, Jaaru found 18 new bugs in popular PMDK and recipe benchmarks. We made Jaaru available on our website for the public usage. Thank you guys for listening to my talk.